As a general rule, as the difference in pressures increases, the amount of draft in the furnace also increases. The pressures in various areas of a furnace are typically measured by instruments called draft gauges. Draft gauges commonly indicate pressure measurements in units of inches of water. These gauges are used to determine the flow of air and combustion gases through the furnace. In a natural draft furnace, the height of the stack affects the amount of draft that can be produced. In general, if all other airflow conditions are equal, the taller the stack, the greater the draft. This is because a taller stack creates a greater difference in pressure. Often, the amount of draft must be adjusted for proper operation of the furnace. Since the height of the stack cannot be adjusted, another technique is used. In some furnaces, the draft is controlled by the position of a damper inside the stack. Changing the position of the damper makes the outlet for the combustion gases larger or smaller. As the outlet gets smaller, draft decreases. As the outlet gets larger, draft increases. Air and combustion gases are moved through forced draft furnaces by fans. This is a simplified illustration of a forced draft furnace. A fan, called a forced draft fan, draws air from the atmosphere and forces it into the furnace. On this furnace, the burners are mounted along one wall. The combustion gases flow through the furnace and then out through the stack. In a forced draft furnace, airflow is controlled by coordinating the positions and operation of the stack damper, the burner registers, and the fan. Some forced draft fans have dampers or louvers on the discharge side of the fan. These dampers can be opened or closed to allow more or less air to flow into the furnace. On other types of forced draft fans, the dampers are located on the inlet side. Adjusting the inlet dampers increases or decreases the amount of air that is admitted to the fan and into the furnace. Another type of furnace is a balanced draft furnace. A balanced draft furnace is similar to a forced draft furnace, but it has another fan in addition to the forced draft fan. The second fan is called an induced draft fan. It is located in the flow path of the combustion gases between the furnace and the stack. So, in a balanced draft furnace, one fan provides air for the burners, and the other fan removes the combustion gases. Furnaces are used to heat many different types of process fluids. As the process fluid circulates through the tubes inside the furnace, it receives heat that is produced by burning fuel. This particular furnace is floor-fired. The process fluid enters the furnace through these tubes in the convection section. This arrangement allows the fluid to be preheated by the combustion gases before it reaches the radiant section of the furnace. Preheating the process fluid makes it possible to bring it up to the desired temperature while burning less fuel. In other words, it makes the furnace more efficient. From the convection section, the process fluid passes through the tubes in the radiant section. The process fluid becomes hottest in the radiant section because more heat and higher temperatures are available. Regardless of the design of the furnace, the tube arrangement has to allow for a continuous flow of process fluid. For example, these tube ends are connected with tubing bends. In other tube arrangements, the tubes are connected together by enlarged sections of pipes called headers instead of tubing bends. The route that the process fluid takes as it flows through a furnace depends on the design of the furnace. Each continuous, uninterrupted path that the fluid takes is called a pass. This furnace is a single-pass furnace, but many furnaces are multi-pass. The flow rate of process fluid through a furnace is regulated by valves. There's usually a control valve for each pass. These valves are often operated automatically as part of a control system. The proper flow of process fluid is critical to proper furnace operation. Flow problems can lead to heat transfer problems as well as equipment damage. One type of problem that can occur is called coking. Coking is the accumulation of carbon deposits on the inside walls of the tubes. Crude oil and some other types of process fluids tend to leave carbon deposits behind as they're heated and flow through the tubes. Coking makes the inside diameter of a tube smaller, and it can restrict the flow of process fluid. It can also lead to heat transfer problems. Carbon deposits insulate tube walls, which reduces the amount of heat that is carried away from the tube by the process fluid. If this situation is not corrected, the tube could overheat, weaken, and eventually rupture. Coking can also develop if the burner flames come into contact with the tubes. This problem is called impingement. Impingement can create hot spots on the tubes that can lead to the formation of carbon deposits. If the impingement problem is not corrected, the tubes could eventually rupture. In multipass furnaces, the flow of fluid through the tubes can present additional problems. In addition to flowing at the proper rate, the process fluid should move evenly through all of the tubes in the furnace. If the flow is not even in all the tubes, the fluid will not be heated evenly. As a result, the temperature of the fluid leaving the furnace may not be within the specified range. Also, if the process fluid moves too slowly in a furnace, the likelihood of coking and its associated problems could increase. In this topic, we looked at how air flows through natural draft furnaces, forced draft furnaces, and balanced draft furnaces. We also looked at how process fluid circulates through a furnace and at conditions that affect flow through the tubes in a furnace. Now let's try some practice questions on this material. Inside this furnace, tubes carry the process fluid through the furnace. The process fluid enters the furnace in the tubes near the stack, passes through the tubes, and leaves near the bottom of the furnace by the burners. The tubes in this furnace are grouped into two major areas. This area, which is closer to the stack, is called the convection section. And this area, which is closer to the burners, is called the radiant section. All of the parts and systems associated with a furnace are used to accomplish one basic task: heating a process fluid. We can get a better understanding of how this is done if we break the furnace operation down into three basic actions. In the first action, air and fuel are introduced into the furnace and then mixed together by the burners. The mixture is ignited at the burners. As the fuel burns, a chemical reaction occurs and heat is produced. In a furnace, heat is produced by the combustion of fuel. Basically, combustion is the process of burning. In order for combustion to occur, four requirements must be met. Combustion requires fuel, air, heat, and a chemical reaction. When all four requirements are met, combustion will occur. We'll use this container of water and dye to show how natural convection works. When heat is applied to the container, the water that's closest to the bottom of the container is heated first. As the temperature of the water near the bottom increases, that water becomes lighter or less dense, and it moves upward in the container. At the same time, the water near the top of the container, which is cooler and heavier or denser than the warmer water, moves toward the bottom of the container. This is what happens during natural convection. As heat is transferred to the water, a difference in density is created. This difference in density causes the water to circulate in the container, and the circulation helps to transfer heat throughout the water. One type of furnace is a balanced draft furnace. A balanced draft furnace is similar to a forced draft furnace, but it has another fan in addition to the forced draft fan. The second fan is called an induced draft fan. It is located in the flow path of the combustion gases between the furnace and the stack. So, in a balanced draft furnace, one fan provides air for the burners, and the other fan removes the combustion gases. This particular furnace is floor-fired. The process fluid enters the furnace through these tubes in the convection section. This arrangement allows the fluid to be preheated by the combustion gases before it reaches the radiant section of the furnace. Preheating the process fluid makes it possible to bring it up to the desired temperature while burning less fuel. In other words, it makes the furnace more efficient. From the convection section, the process fluid passes through the tubes in the radiant section. The process fluid becomes hottest in the radiant section because more heat and higher temperatures are available.